Hello students, in this video we're going to talk about measurability in the sense of Lebesgue. In measure theory, there are two major forms of measurability. That is, measurability can be defined in two major ways. It could be defined in the sense of Lebesgue and it could be defined in the sense of caratheodory theory. Okay, but in this video, let's clearly look at how we can define it using the concept of, we want to prove, to be precise, we want to prove some propositions on measurability of sets in Lebesgue sense, and you look at whether there is equivalence between measurability in the Lebesgue sense and caratheodory. So now we start with the first proposition. Let's see proposition 1. Proposition 1. What does that say? It says if A is measurable, if A is measurable in the sense of Lebesgue, so its complements, A complement, which is equals to R, difference A, is also measurable. How do we prove this? Beautiful. Now to prove this, it will start by saying that let F be a closed set and U be an open set, such that F is contained in A and A is contained in U. Okay, yes, let's say that. Okay, now you observe that we said F is closed and U is open here. Then F complement will be superset of A complement with superset of U complement. With this time around now, with introducing the complement, F that was originally closed will be what? With FC open, F complement open, and U complement closed. Okay, so let's clean this so that we continue. Closed. So now to continue with this, note that F complement is what? Is open now, and the U complement is closed. Okay. So from there, we can say that then F complement difference U complement is the same thing as A complement, or let's say it's contained in A complement. Yes, you check it, which is the same thing as U difference F. And from the concept, from the proposition, it implies that since A is measurable and U complement is the same thing as U difference F, this implies that this now implies that the A complement is equally measurable, because initially we have assumed that A is measurable, and from this concept now we are equally saying that the A complement is the same thing as U difference F, which is equally measurable. So this proposition 1 is complete. This is complete. Proposition 1 is complete. So let's look at another proposition. And see how simple this proposition is. Let's look at another one. Now another proposition here. If proposition 2, if A and B are measurable in the sense of Lebesgue, so is A intersection B. Fine. Okay. Now, I want to show that if A and B are sets that are measurable in the sense of Lebesgue, their intersection is also measurable. So let's start with let epsilon greater than 0. Let epsilon be greater than 0. That is, we need an epsilon. We choose from the concept of F is contained in A is contained in U that we used before. You can now take that U contains A contains F. I hope you understand that. Yes. Okay, U contains A contains F. So, which implies for set A, it can be U A contains A contains F A. That is for set A. Whereas and also U B contains B contains F B from this concept. Okay. I hope we understand that. So therefore, the measure of UA difference FA, basically from what we had earlier said, let's say is bounded by epsilon over 2. Yes, epsilon over 2. And measure of B, let's say UB difference FB is equally bounded by epsilon over 2. How do you arrive at epsilon over 2? Now the initial epsilon must be positive, and now we are talking about two sets, so we want to divide them into two parts so that by the time we add them up together, it will give us epsilon. That's our target here. So, and we got this from the previous concept in our promotion 1, that if we have this, we can turn it over that U will now be superset of this A. I hope that is clear. Now this UA with this continuity is taken with respect to set A, and UB is taken with respect to set B. So now, and originally before we said A in our promotion 1, we said A complement is U difference F. So we can use that concept here to equally look at the complement of that set, which is going to be what? UA, and this simply means that what? This UA is what we are measuring here, not FA. FA is not it, it is UA. The same thing goes to UB here. I hope that is taken now. Okay. Now, we just have a little more thing to write and complete the theorem. Now bring them together as what? We bring them together as intersection. Because we are dealing with intersection of sets. So we bring them together now as intersection. I want to show that the intersections are equally measurable. I hope you are following. Okay. Now we can say that then U A intersection U B, we contain A intersection B, and this will contain F A intersection F B. I hope that is taken based on what we have done before. And U A now difference U B, splitting it now, will be equal to our difference F A intersection F B. How do we arrive at this? We had originally said that U difference F, which is the complement of our A that we obtained the other time. So we now be what? Will be a subset of UA difference FA. I hope that is taken. Union UB difference FB. So this implies that in the previous proposition we said if A is Lebesgue measurable, its complement is Lebesgue measurable. Now this is the complement of UA. This is the complement of UB. So the union of the two of them has implied that when they form intersection, we are talking about Lebesgue measurable sense. Their complement will be measurable as well. And when their complement is measurable, equivalently, it means their intersection is measurable. So that is what we have shown here. So with this, we have come to the end of this second proposition. Stay blessed as we look at the other one. Now, let's look at the last one for this video, and that is the definition of what? Measurability in the caratheodory sense. looking at definition of measurability in caratheodory sense. Now we have proved vital propositions about measurability in the sense of what? In the sense of Lebesgue. Now I want to look at measurability in the sense of caratheodory theorem or theory. Now, a set E in R, let's say we use just one-dimensional example, is said to be measurable in the sense of caratheodory. The sense of caratheodory, if for another subset A in that set of real numbers, okay, we have the outer measure of A, is equal to the outer measure of A is equal to the outer measure of A intersection E plus the outer measure of A intersection E complement. So if this happens, then we say that the set E is measurable in the sense of caratheodory. So if the outer measure of another subset of that real number now intersects the outer measure of A together with the complement of E. So now there is a theory that says that a set is measurable in the sense of caratheodory if and only if it is measurable in the sense of Lebesgue. So that's a theory that brings the two of them together. That is, a set is said to be measurable in the sense of caratheodory, and if and only if it is measurable in the sense of Lebesgue. So with this, we have come to the end of these important theorems or propositions in Lebesgue's theory. Do well to click on the notification bell so that each time I upload the video, you'll be duly notified. God bless you.